Okay, students. So now we'll try to understand what happens in an electrochemical cell. So as we discussed, you all know there is a chemical reaction taking place in a cell that leads to the production of electricity. So that is why we call them as electrochemical cells. So in electrochemical cells, there are two terminals, the positive and negative terminals, and they are referred to as electrodes. The positive and negative electrode when we look at the function of a cell. So to understand that, first we will do this simple activity where we have a metal that is zinc metal. Here you can see this is a zinc metal. And here I have sulfuric acid. So you are familiar with acids. Sulfuric acid is a concentrated acid. So in the solution, it dissociates to form H plus ions and sulfate ions. And zinc is a metal. So if we put this metal strip, that is zinc strip, into sulfuric acid, you all have to observe what happens under the solution. Can you all see the evolving of gas bubbles? The gas bubbles are liberated. Around the metal strip, you can see that. Even if I rotate, you will be able to see the gas bubbles. Here you can see. So this is how an electrode functions. Now, like I said, sulfuric acid dissociates to form H plus ions and sulfate ions. At the same time, now zinc is a metal that has the positive nucleus and the negative electrons. You all know in a metal, the electrons are free. So when zinc is put into sulfuric acid, what happens? Hydrogen gas is liberated. That is what you see here. Around the zinc metal, you can see the hydrogen gas. So that is because H plus ions from sulfuric acid take up electrons from the zinc metal and then they get converted to hydrogen gas. At the same time, can you all observe the zinc metal? You will not see a color change, but you can see the zinc metal becoming more clear. If you compare the top part of the metal and the bottom part of the metal, you will see a difference in their color. The bottom, which is under the solution, becomes more shinier. That is because the zinc plate or the zinc metal dissolves. So here zinc is dissolving and hydrogen gas is being evolved. So those are the changes taking place in this particular system. And this system where we put a metal into an acid is known as an electrode. So this is a zinc electrode. Okay, students. So in the previous activity, you all saw how or what an electrode is. When we dip a zinc metal into sulfuric acid, you were able to see the gas bubbles evolving. So I explained to you all that the zinc metal, it undergoes oxidation. We didn't use the term there, but you all are familiar with the term. Oxidation means a species loses electrons and becomes the product. So here zinc metal loses electrons and becomes zinc 2 plus ion. So that is oxidation taking place. And inside the sulfuric acid, there is H plus ions, sulfate ions and OH minus ions. Their H plus ions take up electrons from the zinc metal and get reduced. That is, they become H2 gas. So that is why you were able to see the evolving of gas bubbles near the zinc plate. So there is a transfer of electrons. Zinc metal loses electrons, hydrogen gains electrons. So if we can make these electrons to move through an external conductor, say the conducting wires, then of course we can make electricity to flow. So that is how we are going to do this activity. We are trying to make the electrons to flow through a conductor, an external conductor. To do that, we need two electrodes. So we have a zinc plate here and copper plate there, two metals, zinc and copper. And the electrolyte solution is the same. It is sulfuric acid. It can conduct electricity, and here I have an ammeter. So ammeter, you all can see it is connected to the two metals, and if we dip the metals in sulfuric acid, you will see the change taking place. You have to observe the metals as well as the ammeter. So here I am going to dip both the plates, and we should make sure that they don't touch each other so that you can see the changes taking place. Now as I dip the metals, you were able to see that near the zinc electrode there is like bubbles forming. That is because you all know, you're familiar with the activity series, students. The zinc metal is more reactive. Because of that, there is a certain amount of reaction taking place. But we are concerned with the reaction that is related to electrochemical cell. So you all can see the ammeter shows a reading. There is a deflection. So that means there is current flowing. And now you can see, here you can see near the copper plate also there are gas bubbles evolving. So the zinc plate is dissolving. That is one observation. And you can see gas bubbles evolve near the copper plate. Can you all see that clearly? At the same time, there is a deflection in ammeter. So that means current is flowing through the external circuit. Is that clear to you all, students? So there is the zinc plate that dissolves, that reacts, and also near the copper plate there are gas bubbles evolving, and at the same time there is deflection in the ammeter. So if there is deflection in the ammeter, that means current is flowing through the external conductor. So when you dip two electrodes into a particular solution, that is sulfuric acid, we dip copper and zinc. There is a chemical change taking place. Zinc gets converted to zinc 2 plus ions. At the same time, near the copper, there is hydrogen, that is H plus ions, being converted to H2 gas. So there is a transfer of electrons. H plus ions take up electrons and become H2 gas. Zinc loses electrons and becomes zinc plus ions. So these electrons travel through the external conductor. That is why there is a flow of electricity and you see the deflection in ammeter. So in this, we had a chemical reaction taking place when we dip both zinc and copper into sulfuric acid, and due to that chemical change, there is electricity generated. That is what we call as an electrochemical cell. So for the electrochemical cell to be complete and for current to flow, electricity to flow, you need to have two electrodes. That is what you need to remember here. And also, students, since zinc metal dissolves, the zinc 2 plus ions go into the solution, leaving the electrons in the zinc metal. So because of that, the zinc metal becomes negatively charged. At the same time, hydrogen takes up electrons from copper. So because of that, copper is going to lose electrons. Therefore, copper becomes positively charged. So copper is positively charged, zinc is negatively charged, and near the zinc, it is oxidation. Zinc losing electrons. Because of that, we call the zinc metal as the anode, and near the copper metal, hydrogen is taking up electrons and becoming hydrogen gas. That reaction, that is a half reaction, that is known as reduction. And reduction takes place near cathode. So here cathode is positive and reduction takes place there. Near the zinc plate, oxidation occurs, therefore it is the anode, but since the electrons accumulate there, the anode becomes negatively charged. And you all know electrons flow from negative terminal to positive terminal through the external circuit. At the same time, electricity flows from positive terminal to negative terminal. That is how the electrochemical cell works. So students, you all saw three observations. You saw the zinc plate dissolve, you saw the gas bubbles evolving near the copper electrode, and also you were able to see the deflection in the ammeter. So deflection in the ammeter confirms that there is a current flowing through the external conductor. And in these two, there are chemical changes taking place. So gas bubbles, it is hydrogen gas, H plus ions taking up electrons, getting reduced, and therefore we call the copper electrode as the cathode. Wherever reduction takes place, it is cathode, and here it is the positive electrode. And zinc dissolves. So there zinc becomes zinc 2 plus ions. So therefore that is an oxidation reaction. So because of that, it is the anode. And here in anode, that is the zinc plate, there is electrons. So anode becomes negatively charged. So these are the observations of this activity. To confirm this observation again, what we will do is, instead of an ammeter, we will use a galvanometer. You are familiar with the galvanometer. There you can, from the deflection, the direction of the deflection, you all know how the current flows in the circuit. So I will remove the ammeter, connect a galvanometer and show you all what happens there. So now I have the galvanometer connected. Here you can see, you know the difference. This is a center zero galvanometer. So current, the deflection can take place in this direction towards this direction. That means the current flows this way from copper to zinc. If the indicator moves in this direction, that means current flows from zinc to copper. So that is what you need to observe. When I put the two electrodes, the metals, that is zinc and copper, into dilute sulfuric acid, you have to observe the direction of the deflection. So here students, when we dip the two electrodes, that is zinc and copper, you all know zinc is the negative electrode or the anode, and copper is the cathode, positive electrode. So when we dip it in, you can see the direction of the galvanometer. Now I am taking it out, and when I dip it, you can see the direction of the galvanometer. So if you look at the direction of the galvanometer, it moves towards this direction. That means current flows this way. So here current goes into the copper electrode. In the solution, current flows from copper to zinc. Copper is positive, zinc is negative. So that also you all know. Current flows from positive to negative. So that is the convention. You all have to understand that convention. In the solution, the conventional current flows from positive terminal to negative terminal. So it goes in this direction. That's why you see the galvanometer also deflect in the same direction. If I put it again, observe the direction clearly. Copper is the positive terminal, zinc is the negative terminal. So the current flow is in that direction, positive to negative terminal. So I am sure students, in this process, that is the process of electrochemical cell. Now here we are trying to understand the function of an electrochemical cell. A chemical reaction leads to the flow of current. So the zinc electrode, there is oxidation taking place. So it is the anode, and because the zinc metal loses electrons, electrons get accumulated in the zinc plate, this becomes negatively charged. At the same time, hydrogen ions from the solution go towards the cathode, that is the copper metal, where they take up electrons from copper and become H2 gas. So copper loses electrons and becomes positively charged. So copper cathode is the positively charged electrode, and current flows from positive terminal to negative terminal, while electrons flow from negative terminal to positive terminal. That is how the electrochemical cell works. And students, for the same activity, now we use the ammeter where you saw the reflection, so you know that current flows through the cell. Then now I have used the galvanometer, that also can be used, and here you can see the direction of the current. Instead of these two, we can also use a bulb to observe that current flows through the cell. So here we have the solution, that is sulfuric acid, and zinc and copper as the metals or the electrodes. Then we call this cell as a simple cell or simple voltaic cell. So to understand the function of the simple voltaic cell a little bit more, what I will do is I will replace the galvanometer with a light bulb. There also you can see the change. Those are different ways of observing that the current flows through the cell or current is generated by a chemical reaction. So to do that, we'll replace the galvanometer with a bulb and observe the function of a simple cell. So here students, again I have taken sulfuric acid, dilute sulfuric acid into a larger beaker so that I can insert the two metal plates. Here you can see this is a zinc metal. That is one electrode, the negative electrode or the anode. And here we have copper. So this is the positive electrode which is the cathode there. Then here the bulb is connected to both the electrodes. You can see that. And the electrodes are connected to a wooden plank so that it's easy to handle the electrodes. Now when I dip the two electrodes into the sulfuric acid solution, you all have to look at the bulb as well as you can see the other observations also. So now I will dip it into the solution. Can you see the bulb lighting? Can you see the bulb lighting? You all were able to see that the bulb lights. When I insert the two metals, zinc and copper, into dilute sulfuric acid, you were able to see the bulb light. So we have looked at three different ways in which you can observe the function of an electrochemical cell. So by a chemical reaction, electricity is produced. For the chemical reaction to take place and electricity to be generated, we need two electrodes. One has to be the anode where the oxidation takes place and that becomes the negative electrode. And the other electrode is the cathode where the reduction takes place and that is the positive electrode. So here zinc is the negative anode and copper is the positive cathode. And electrons flow from negative terminal to positive terminal or the negative electrode to the positive electrode, while current flows from conventional current flows from positive terminal to negative terminal. So we can confirm the flow of current either by using a bulb, a galvanometer or an ammeter. So from all these students, I am sure you all can understand clearly the function of a simple electrochemical cell. Okay students, so now these are different types of electrochemical cells. When I say different types, you can change the metals that we dip in sulfuric acid. So to understand that, here I have sulfuric acid, then I have two metals. You all can see this is an iron nail. So one metal is going to be iron, the other metal is copper. And both are connected to the galvanometer. So you can see the deflection of the galvanometer as well as you can see the direction of the current flow as well. So far you all are familiar with what happens in an electrochemical cell. There is a chemical reaction taking place and due to the chemical reaction there is flow of electrons. That means there is a flow of current. And you all know always electrons flow from the negative terminal to the positive terminal and current, that is the conventional current, flows from the positive terminal to the negative terminal. And you are familiar with the half reactions or the half ionic reactions. The oxidation reaction is where a species loses electrons and becomes either a positive ion. So here a metal loses electrons and becomes the positive ion. So that is an oxidation reaction and where oxidation takes place is known as the anode. And when a species takes up electrons and becomes the product, say for example H plus ions taking up electrons and becoming H2 gas, that is a reduction reaction. And reduction reaction occurs at a metal electrode and that electrode is known as the cathode. And from the previous activity, you all can remember students, the cathode is positively charged and anode is negatively charged. Now we have both iron and copper electrodes. First we will see what happens when we dip those two in sulfuric acid. So I am going to dip the two electrodes into sulfuric acid, copper and iron. Now you saw the deflection of the galvanometer. Here you can see how it deflects. And also you will see observations near the two electrodes. We will have to wait for some time. When you put the metal rods or metal plates into the solution, we have to make sure that the metals do not touch each other. They have to be dipped in the solution. We will have to wait for some time to see the change. So here also, from the deflection of the galvanometer, you all know current flows from copper to iron. At this point, students, recall the activity series. In the activity series, you all know iron is above copper in the activity series. That means iron is more reactive than copper. So because of that, when we have iron and copper, iron will dissolve. Iron will get oxidized. That is, Fe atoms lose electrons and become Fe2+. So there, the iron nail will become the negative electrode, and that is the anode because oxidation takes place there. At the same time, H+ ions from sulfuric acid will migrate towards the copper metal, and from there H+ will take up electrons and become H2 gas. So here, students, can you all see the gas bubbles evolving near the copper plate? So there what happens? H+ ions from sulfuric acid, because sulfuric acid dissociates and H+ ions are released. H+ ions come near the copper metal. There they take up electrons from copper and get converted to H2 gas. So that is what you can see as the gas bubbles near the copper plate. But iron acts as the anode. So students, you all can see now near the iron you don't see any gas bubbles. So iron nail acts as the anode. There iron dissolves. So iron gets converted to Fe2+ ions and it goes into the solution, leaving the electrons in the iron nail. So there iron becomes negatively charged, and because it is oxidation, iron is the anode. And near the cathode, H+ ions from the solution come towards the copper plate, and there they take up electrons and get reduced, and that is why you can see the evolving of gas bubbles. So there it is a reduction reaction. The copper metal acts as the cathode and that becomes positively charged. So in an electrochemical cell, cathode is positively charged, anode is negatively charged. And when we use copper and iron, copper is the cathode and iron is the anode. So those are the observations. So now you all can understand that, students. So here we use two different metals, iron and copper. In the activity series, you all know iron is above copper in the activity series. That means iron is more reactive than copper. So there, iron, because it is more reactive, it acts as the anode. It undergoes oxidation, whereas copper is less reactive, so it does not undergo oxidation. So there will be reduction taking place near cathode, that is copper. Because copper is less reactive, it is reduction near the copper electrode. Iron is more reactive, so there is oxidation taking place near the iron metal. Is that clear to you? So always remember, students, when we take two metals as electrodes in an electrochemical cell, the more reactive metal becomes the anode. It dissolves and it undergoes oxidation reaction, therefore it acts as the anode. The less reactive metal, near that it is the reduction taking place, and therefore the less reactive metal becomes the cathode. And also the cathode is positively charged and the anode is negatively charged in an electrochemical cell. So those are the things that you all have to understand. Then after this, we will discuss the half ionic reactions. That is the reduction half reaction and the oxidation half reaction taking place near the cathode and anode respectively when I discuss the observations with you all. Okay students, so this is the third electrochemical cell that you are going to observe. Here again we have dilute sulfuric acid as a solution, and then I have the galvanometer, and here you all can see I have two different metals. One is iron, the other one is zinc. So when you compare the reactivity of iron and zinc, you all know iron is less reactive than zinc, or zinc is more reactive than iron, and in the activity series also zinc is above iron. So from the previous activities and the observations, now you all can understand students, the more reactive metal, so that is zinc, will undergo oxidation. Therefore that will become the anode, and also that will be negatively charged. And iron, which is less reactive compared to zinc, will undergo, or the reaction that happens near iron will be the reduction reaction. Therefore, iron will be the cathode, and iron will become the positive electrode. So, you are familiar with all those. So, the current flows from positive terminal to negative terminal. That can be observed from the deflection of the galvanometer. And also you can see the other observations as well. So here I am going to dip the two electrodes into the solution. You can see the observation of the galvanometer, how the indicator deflects, and the observations near the electrodes. So this is zinc and iron. So now I have inserted both the metals zinc and iron into the sulfuric acid solution. So as you know, zinc is more reactive, so that has to undergo oxidation. The zinc plate will dissolve. It will react with sulfuric acid, it will dissolve, and it will become negatively charged. And iron, near the iron, because iron is less reactive than zinc, near the iron, hydrogen ions undergo reduction. So can you all see? Near the iron nail, you can see the gas bubbles. So those are the hydrogen gas bubbles. And also you will be able to see that the zinc metal dissolves. And from the galvanometer, you can see the current flows from iron to zinc. Iron acts as the positive electrode, zinc acts as the negative electrode. Iron is the cathode and zinc is the anode. So their current flows from iron to zinc. That is how the galvanometer deflects. That you can understand. So these are the observations, students. Near the iron nail, you see gas bubbles evolving. That is hydrogen gas. Zinc metal will dissolve. So zinc will be the anode. It will be negatively charged. Iron will be the cathode. It will be positively charged. And current flows from iron to zinc. That is how this particular electrochemical cell works. So from these, students, from all three activities, we use different metals, different combinations of metals. So first thing you have to remember the activity series, which metal is more reactive. The more reactive metal acts as the anode because it undergoes oxidation. So here zinc is more reactive than iron. Zinc undergoes oxidation, it becomes the anode and it becomes negatively charged. At the same time, since iron is less reactive, hydrogen ions, H+ ions, come towards the iron, and there it takes up electrons from iron metal and it gets reduced. Hydrogen H+ ions get reduced by taking up electrons from the iron metal. So their iron metal or the iron nail acts as the cathode. So you were able to see gas bubbles evolving near the iron nail, and you were able to see the direction of the current flow as well. So from this, you all can understand the way the electrochemical cell functions when we use iron and zinc as electrodes. Okay, students. So now we will try to understand the solutions that conduct electricity. So we discussed what electrolysis is. By passing electricity, by supplying electricity, if we can bring about a chemical change in a solution or a liquid, then that process is known as electrolysis. So for this process to happen, the solution or the liquid should conduct electricity. So that is what we are trying to figure out now. So I have a set of solutions here. You can see this is coconut oil, then we have kerosene, then there is distilled water, there is acidified water, salt solution, and finally ethanol solution. So we'll try to observe the solutions that conduct electricity and the solutions that do not conduct electricity. So to do that, we need an ammeter to observe whether a current is flowing through the solution. Then I have connected the ammeters to carbon or graphite electrode. The carbon graphite is a good electrode, and you all know it is an inert electrode. Why do we call it an inert electrode? Because the carbon graphite does not react with any of the chemical substances that we are going to use here. So both graphite electrodes which are inert, and the electrodes are connected with the dry cells. So we have two dry cells here. So this is what I am going to do. First I'll take one solution, then dip the electrodes into it, and we have to make sure that the two electrodes do not touch each other inside the solution. Because if that happens, current can flow through the graphite electrodes. So we have to keep them apart, and then you have to observe the ammeter reading. Thereafter, you need to wash the electrodes, dry them, and then you put it into the next solution. So that is how I am going to repeat the procedure with all the solutions. So first we'll take coconut oil, and I will put the two electrodes. Now here you can see ammeter reading is 0. When we dip it in, you have to look at the deflection, whether there is a deflection or not. So here if I dip the two electrodes, is there a change in the ammeter? There is no change in the ammeter. So here I have both the electrodes inside, no change in the ammeter. But like I said, if we touch this, you can see there is a deflection. So that means inside the coconut oil. Now when I dip it inside the coconut oil, there is no deflection. That means current does not flow through the coconut oil. So we have to clean it first. Now we will use the second solution or the liquid, that is kerosene. So here we have kerosene. Again I am going to dip the two electrodes. You have to look at the ammeter. The two electrodes should not touch each other. Look at the ammeter. Do you see a deflection? No, there is no deflection in the ammeter. So here you don't see a deflection. That means there is no electricity passing through kerosene. Now here also if I touch the electrodes, you can see the current flow. But inside the liquid, that is kerosene, there is no current flow. That means kerosene does not conduct electricity. So I have cleaned the electrodes. Then we will use the next solution, that is distilled water. So into this also I'll be dipping the two electrodes. Electrodes are not touching each other. Can you see a deflection? No, there is no deflection in the ammeter. So that means the distilled water does not conduct electricity. So all three liquids, that is coconut oil, kerosene and distilled water, they do not conduct electricity. So these solutions that do not conduct electricity are known as non-electrolytes. We will do the activity with the other liquids and solutions as well. Now I am going to use acidified water. You're familiar with acidified water. We add a small amount of sulfuric acid to distill water. Then we will get acidified water. So now I am going to dip the electrodes into acidified water. Here, if we dip the electrode, can you all see the deflection there? So here, when I don't dip it, there's no reading. But when I dip the electrodes, you can see a deflection. So that means current or electricity is being conducted through acidified water. So acidified water conducts electricity. Then it is known as a electrolyte solution. It is an electrolyte solution. Acidified water conducts electricity. I will have to wash the electrodes. We have to clean the electrodes. So I'll dip them in distilled water. And we will have to dry them. So then I'll use the next solution, that is salt solution. So salt solution also we will see what happens. Now when I dip the electrodes, here now the reading is 0. When I dip the electrodes, you can see a deflection. So again, if I try that, you can see the deflection there. So that means salt solution also conducts electricity. We'll wash the electrodes again. And then the last solution, that is ethanol. Again, if I dip the electrodes into ethanol, do you see any change? Is there a deflection? No. So that means ethanol also does not conduct electricity. So we tried with all these solutions. Out of these, when we used acidified water and salt solution, you were able to see a deflection in the ammeter. So that means salt solution and acidified water conducts electricity. Those solutions are known as electrolyte solutions. Whereas coconut oil, kerosene, distilled water and ethanol, there is no deflection when you dip the electrodes. So that means they don't conduct electricity and they are known as non-electrolyte solutions or liquids. So from these students, you will be able to understand that some solutions conduct electricity and those are the electrolyte solutions, and some liquids or solutions do not conduct electricity and those are the non-electrolytes. So for the electrolysis process, we will be using electrolyte solutions. Okay students, so now we will observe what happens when we carry out the process of electrolysis with a solution of sodium chloride. That is an aqueous solution of sodium chloride. Sodium chloride salt dissolved in water. Aqueous sodium chloride solution. So here I have aqueous sodium chloride solution. I have the two dry cells connected together and the carbon electrodes. You all know carbon graphite electrodes. Those are inert electrodes. That means they do not react with the electrolyte solution. So the inert graphite electrodes are connected to the dry cell. So here you can see the positive terminal. So this red color wire connected to this electrode, that is the graphite electrode, because the positive terminal is connected to this electrode, this becomes the positive electrode. And here this is the negative terminal of the battery. So the black color wire that is connected to this electrode, so this becomes the negative terminal. So we have the positive graphite electrode and the negative graphite electrode. So this you all know in electrolysis, when you connect the electrodes to the dry cells, depending on the terminal, the electrode becomes positively or negatively charged. So we have the positive and negative electrodes. Now we'll take the solution, sodium chloride solution here, and when we dip the electrodes into the solution, you all have to observe what happens near the electrodes and in the solution. So here again we have to make sure that the electrodes don't touch each other inside the solution. So I'm dipping both the electrodes into the solution. We need to give some time for the reaction to occur. Observe the electrodes. Okay, students. So if you look at the electrodes very closely, can you see near this negative electrode, you can see clearly the gas bubbles being evolved. The gas bubbles being liberated near the negative electrode, and near the positive electrode also you all can see the evolving of gas bubbles. Can you all see the gas bubbles near the two electrodes? Both the negative and positive. This is the red color one is the positive electrode, where I have clipped the black color one is the negative electrode. Can you see gas bubbles near both the electrodes? Is it visible to you all? So what happens in the solution? Now in the solution, there is sodium chloride and water. So sodium ions, Na plus ions, Cl minus ions from sodium chloride, and H plus ions and OH minus ions from water. So near the positive electrode, the negative ions are attracted to the positive electrodes. So near the positive electrode, there will be OH minus ions and Cl minus ions. At the same time, near the negative electrode, there will be positive ions attracted. So H plus ions and Na plus ions. So out of those, near the positive electrode, it is the chloride ion, Cl minus ion, that is going to lose electrons and get oxidized. When a species releases electrons, we call it oxidation. So chloride oxidizes to form chlorine gas. Near the positive electrode, chlorine gas will be evolved. At the same time, near the negative electrode, the H plus ions take up electrons, they get reduced and they evolve as hydrogen gas. So near the negative electrode, it is hydrogen gas. Near the positive electrode, it is chlorine gas. So when we electrolyze sodium chloride aqueous solution, you will see gas bubbles evolving at both positive and negative electrodes, and near the positive electrode it will be chlorine gas, and near the negative electrode it will be hydrogen gas. Is that clear to you all? So you all should know the observation. Okay students, so now we will observe what happens when we try to electrolyze an aqueous solution of copper sulfate. So an aqueous solution of copper sulfate is an electrolyte solution. It conducts electricity. So you all know the color of copper sulfate. It is a blue color solution. So copper sulfate solution. Now when we say copper sulfate solution, copper sulfate is dissolved in water. So there are ions, Cu2 plus ions and H plus ions. Those are the positive ions or cations present in the solution. Then there is hydroxide ion from water, OH minus, and sulfate ion from copper sulfate. Both are negative ions or anions. Then I have the dry cell here. This is a 9-volt battery. You can see the terminals. The negative terminal is connected to this carbon graphite electrode. So this becomes the negative electrode, or what we call as the cathode. You all know students, the electrode near which the reduction process takes place is known as the cathode. So here the negative electrode is the cathode. So the reduction will take place near cathode. And here you can see the positive terminal that's connected to this electrode. So that becomes the positive electrode, and there it is known as the anode. Anode is the electrode where oxidation takes place. That is the convention. You all are familiar with that. And also you all already know students, the negative ions in the solution migrate towards the positive electrode and the positive ions migrate towards the negative electrode. So now we will see what happens when we dip the two electrodes in copper sulfate. So here I have copper sulfate. You all have to observe the color of the solution since the solution is colored, and also you all have to see what happens near the electrodes. Now here you can see both the carbon electrodes, the graphite electrodes are clean. You see the color of graphite only. Now I will dip them in the solution. We have to make sure the electrodes do not touch each other, and you all have to observe what happens there. It takes a little time for the change to start. Can you all see near the positive electrode? There are small gas bubbles forming near the positive electrode and the negative electrode. So here you all can see, students, near the positive electrode, there are gas bubbles. So near the negative electrode, this is the cathode, that is with the black color clip, that is the cathode. Near the cathode also you all can see a slight color change now. You can see a light brownish color layer forming near the cathode, that is the negative electrode. And near the positive electrode, that is the anode, you can see the liberation of gas bubbles. Can you all see those changes clearly? So students, with time you all can see near this one, the red color clip, that is the positive electrode or the anode, you see the evolving of gas bubbles. You all can see gas bubbles around the electrode. And then the negative electrode, that is the black color clip, there, that is the cathode, you can see the depositing of a brownish color layer. So there are copper deposits on the negative electrode. Copper ions are positive ions. They migrate towards the negative electrode and they take up electrons and deposit as copper metal. So that is a reduction process. So therefore the negative electrode is the cathode there. At the same time, near this red color clip, that graphite electrode is connected to the positive terminal. The negative ions, here we have sulfate ion and OH minus ion, both migrate towards the positive electrode, but out of those, the OH minus ion gets oxidized and there is oxygen gas being evolved near the positive electrode. So near the positive electrode, oxygen gas is evolved. Near the negative electrode, copper deposits. And also with time you all can observe, you would have seen the change to a certain extent. The blue color of the copper sulfate solution decreases. Can you all see a small change there? Initially the color was more intense. Now the color has become a little more lighter. And with time, if you continue doing this process, the color will further decrease. So for that we have to wait for some more time. So here, if I take out the electrodes, you can see the copper deposited on the negative electrode, that is the cathode. That is very clearly visible. Now you can see the color there. The brownish color deposit, that is the copper deposited on the negative electrode. Okay students, now can you all see? Now I have been having the electrodes inside the copper sulfate solution for some time now. Now you all can see a more better color change. You can see the color of copper sulfate has decreased to a great extent compared to the initial solution. So if you continue this process, if we do this electrolysis for a very long time, then of course the color of copper sulfate will be completely disappeared. It will become colorless. So, and at the same time, you were able to see the deposit of copper here. At the cathode, that is the negative electrode, you can see copper depositing, a brown color deposit. At the same time, you saw the evolving of gas bubbles near the positive electrode, that is anode. And also you saw the color decrease. Blue color of copper sulfate decreases with time and finally it will become colorless. So that is what happens when we carry out electrolysis. So this is what happens if we carry out electrolysis of copper sulfate. You can see the copper deposited there. So those are the observations. You have to remember 3 observations. Copper deposits on the negative electrode, gas bubbles evolve near the positive electrode, color of copper sulfate decreases. That is, the blue color of copper sulfate decreases, and if we carry this on for a long time, the color will completely disappear. It will become a colorless solution. Okay students, so now we will see the observations, or we will look at the activity where we carry out electrolysis of acidulated water. What is acidulated water? We take distilled water and to that we add a small amount of dilute sulfuric acid. So then we get the acidulated water. You all know the reason. Distilled water does not conduct electricity. So when we add a small amount of acid, there are free ions generated, and because of that, acidulated water becomes an electrolyte. So because of that, it conducts electricity. So inside this plastic cup, we need a plastic cup. In that I have acidulated water, and here you can see there are 2 carbon graphite electrodes fused from the bottom. From here the connection is given. They are inserted, you make holes in the plastic cup, and through that we insert the graphite electrodes, and then we have to seal the holes so that the water does not leak. Now here you can see there's no leaking of water. So to do that, you can either use silicone gum, PVC, or you can have some kind of adhesive that does not react, but you can use it to seal the cup. So that is how we make the electrolytic cell here. And you all can understand students, this is somewhat different from the previous electrolytic cells that we used. Earlier we used the beaker with the electrode dipped into the solution. But here we have fixed the electrodes to the cup so that we can collect the gases. So to do that, we have 2 small test tubes here. What we need to do is we need to fill this with water and invert it onto the electrode. So to do that, I will fill it with water. We have to make sure there are no gas bubbles, and we have to invert it onto the electrode. So here I have inverted 1 test tube. The same way I will fill the other test tube also with water, and then we invert it and onto the electrode. So this is how we have the electrolytic cell set up there. So then we have a 9-volt battery here. So you can have a look at the terminals, the positive terminal and the negative terminal. And here I have a cover for the battery, so we can connect it easily. Now this side, the positive terminal will get connected to this part here, and the negative terminal gets attached to this part. And here there are 2 colored wires. The black color wire will be connected to the negative terminal like this, and the red color wire will be connected to the positive terminal. So when I attach it this way, there will be current flowing through the electrodes and the cell. So we will see what happens there. You all have to observe the changes taking place near the electrodes. So here I have connected the dry cell. You can see now this wire, black color wire, is connected to blue here. So this becomes the negative terminal and this is the positive terminal. you all can see slowly the gas bubbles starting to evolve. Look at the electrodes closely. Near both electrodes, you will see gas bubbles evolving. So here students, you all can see this side I said is the negative terminal. Can you see the gas bubbles evolving a bit more faster? Here it's not the rate of reaction, it is the volume of gas that is going to be evolved. You will see a difference, you have to notice that as well. Near both electrodes, you can see gas bubbles evolving, but here you can see it coming. We will have to wait for some time until the water gets displaced. When the gas bubbles come up, water is pushed down or displaced down and the gas collects over water. You will be able to see that with time. So in this solution or the liquid, here it is acidulated water, what are the ions present? From water we get H plus ions and OH minus ions. There is a small amount of H plus and sulfate ions from sulfuric acid as well. But here the main ions are H plus and OH minus. So the H plus ion is attracted to the negative electrode and the OH minus ion is attracted to the positive electrode. So that is where the oxidation and reduction will take place. So when H plus ions get attracted to the negative electrode, they take up electrons and they can become hydrogen gas. So that is reduction. So there it is the cathode where reduction takes place. So this will be the negative electrode, the cathode where hydrogen gas is evolved. And on this side, we have the positive electrode. So the OH minus ions gets attracted to the positive electrode and there OH minus loses electrons and gets oxidized. So here oxidation takes place, therefore it becomes the anode. The negative electrode is the cathode and the positive electrode is the anode. So in both you can still see the gas bubbles coming up. We will have to wait and see whether equal volumes of gas is collected or not. Okay, so now can you all see students, after some time, now this is near the negative electrode, that is the cathode. So here you can see more volume of gas has been collected, whereas near the positive electrode, that is the anode, there is less amount of gas collected. So you all can see the difference and still the gas is being collected. Here you can see the gas bubbles moving. Here also you can see the gas bubbles coming up. So still the gas is being collected. Like this, if we keep it for a longer time, you will get more gas being collected inside the test tubes. So we'll wait for some more time. Okay students, so now I let the electrolysis to occur for some time. Now here you can see this of course is about half filled with gas. So here you can see students, the negative electrode, that is the cathode, is completely filled with gas. The test tube that is covering the cathode is completely filled with gas. So you all know this is hydrogen gas and this is oxygen gas. But to confirm that the gas evolved near the negative electrode or the cathode is hydrogen and the gas evolved near the positive electrode or the anode is oxygen, we can carry out the test. You all know the test. When we insert a burning splinter, what happens if it is exposed to hydrogen gas? At the same time, to test for oxygen gas, what do? We insert a glowing splinter. So to do that, I will have to first take out the test tube out of water. But I have to make sure that the gas does not escape from the test tube. So here you can see now I have the gas inside this. So we need to insert a burning splinter into this. Okay, so I have the test tube with hydrogen gas and now I'm going to make a burning splinter. This is a dry eagle. I will hold it to the flame. So while the flame is on, we have to... So you heard the pop sound and the flame goes off. So that is how we identify that it is hydrogen gas. Now still the oxygen gas is filling into the other test tube. We will test that as well. Okay students, so still you all can see the gas bubbles evolving near the negative cathode. So you all know that it is hydrogen gas. We heard the squeaky pop sound when I inserted the burning splinter. Now I have the oxygen gas collected in the other tube, the second test tube, that is covered over the positive electrode, that is the anode. So again I'll have to take out the test tube, making sure that the gas does not escape from the test tube, and then I will need to insert a glowing splinter to observe and confirm whether it is oxygen or not. So now I'm going to take out the test tube, making sure the gas does not... Here I have the gas collected from the positive electrode, that is the anode. So you all know it is oxygen. We have to insert a glowing splinter. So how to burn this? You only need the glow at the tip. And when you insert it into the tube containing the gas, you have to observe what... Can you all see? It rekindles. So you all saw that the glowing splinter rekindles and relights. So that confirms the gas collected in this is oxygen gas. So we did the electrolysis of acidulated water, and from there we saw that you all were able to see that the gas is evolved from both the electrodes, and near the negative electrode there was more volume of gas, or we can take it as double the volume than that is evolved at the positive electrode, and near the negative electrode it is hydrogen gas, because the H plus ions go towards the negative electrode, they migrate towards the negative electrode, there they undergo reduction and become hydrogen gas, and that is what we collected and we confirmed it using the burning splinter. Burning splinter, when you insert it, it burns off with a squeaky pop sound. Then the gas that was collected near the positive electrode, that is half the volume compared to the other gas, and that is oxygen. So there OH minus ions migrate towards the positive electrode, and there it undergoes oxidation, therefore it is the anodic reaction, and we confirm that it is oxygen using the glowing splinter. You saw the glowing splinter relight and rekindle. So from that we confirm the two gases evolved. So those are the observations of electrolysis of acidulated water. Okay students, so now we will do this activity to observe how electroplating takes place. To do that, now here I am going to plate copper onto the metal spoon. So for that we need an electrolyte solution that has the metal that has to be plated. So here we have copper sulfate. You all know the color of copper sulfate, blue color solution. Then I have an iron spoon, normal stainless steel spoon. So onto that we will be plating copper. So we have the anode where oxidation takes place, and here it is going to be the positive electrode, and the cathode where the reduction takes place is going to be the negative electrode. So when we need to electroplate an object, we need to have the object connected to the cathode. So there it has to be connected to the negative electrode. The spoon has to be connected to the negative electrode. So here I have the dry cells. Now you all know the positive and negative terminals. The black color wire is connected to the negative terminal. Red color wire is connected to the positive terminal. So here I will have to connect the object to the negative terminal. So that is going to be the black color wire, and the positive terminal is going to be the copper metal. So the object that has to be plated is connected to the negative terminal, and the metal that has to be plated should be the anode. So here we have a copper plate that is connected to the positive terminal. Now if we dip these two into the solution, that is the electrolyte solution, you will see the change. Here I am going to dip both the electrodes there, object and the copper electrode. You all have to observe what happens. You have to observe the spoon and the copper plate. So here students, you all can see, if you look at the spoon closely, can you see at the edges of the spoon, the outer line of the spoon, you can see a reddish brown color deposit, a brownish color deposit. So you know copper metal is brownish in color, so that dissolves, goes into the solution, and the copper ions from the solution deposit on the metal spoon. You can see the deposit starting to take place on the spoon. Can you all see that clearly, students? The brown color deposit on the spoon. So here you can see, students, now on the spoon you can see the brownish color deposit. So copper, now you can compare. The copper plate dissolves, it goes into the solution, and the copper ions from the solution deposit on the spoon. Has the color changed in any way? Color of copper sulfate solution. Is it the same or different? You can see it's the same color. So because we have copper as the anode, copper ions from anode dissolve and go into the solution. From the solution, copper deposits on the spoon. But the amount of copper sulfate in the solution does not change. So therefore, the color does not change. So if we keep it for a longer time, you will see more copper depositing on the spoon. But here, of course, we have seen the copper deposit. Here you can see the copper deposited around the spoon more clearly. So this is a normal laboratory technique where we try to understand the copper plating or metal plating, or what we call as the electroplating of copper onto the object. You have to connect the object to the cathode. So there copper ions will take up electrons from the cathode, which is the negative electrode, and it will deposit on the object. At the same time, you connect the metal that has to be deposited as the anode. So here this is the positive electrode. So here what will happen is there will be oxidation taking place, that is copper metal will dissolve and become copper ions. It will go into the solution. So because of that, the amount of copper ions, that is copper sulfate in the solution, does not change. So the color of solution does not change. You see the deposit at the cathode, dissolving of the anode, but no change in the electrolyte solution. The color of copper sulfate does not change. So those are the observations that you will get during electroplating of copper to a metal object using copper sulfate solution. Okay, students. So now we are going to do this activity in order to observe whether air is essential for rusting. So to do the activity, I have two boiling tubes here. Then we have normal water. Then I have coconut oil here, a spirit lamp to boil water, and we need iron nails. Now here you can see these are clean iron nails. There's no rusting, clean iron nails. And also, since I bought these from the shop, what I did was I immersed these iron nails in hydrochloric acid for about 15 minutes. The reason is, normally the iron nails that you buy from the shops are coated with zinc. To prevent rusting, they are coated with zinc. So when you dip them in hydrochloric acid, the zinc dissolves. So here we have the iron nail, that is only metal iron. no other coating. So those are the materials that we need. Now we will do the activity. So to do that, I need to take water into both the boiling tubes. So this and the second boiling tube, roughly equal volumes. You don't have to really measure them. We need to have roughly equal volumes of water. This is just to see whether air is required for rusting or not. So one boiling tube, I will place it with water. The other one, we need to boil water. So to boil this water, I'll be using a spirit lamp. So now I'm going to boil water. You can use the Bunsen burner or we can use the spirit lamp. So what happens when water boils? Now we are going to test whether air is essential or not. So normally in normal water there is oxygen and air dissolved in it. But you all know solubility of gases decreases when temperature increases. When we boil water, because the temperature increases, the air that is dissolved in it, the solubility decreases, and because of that air is removed from water. So what we will do is we will boil this water and then we will put a layer of coconut oil over the boiled water. What is the reason? All the air is removed when we boil water, and then to prevent further dissolving of air in water, we have a layer of coconut oil. So that's what I am trying to do now. Now you can see the water starting to boil. So there itself you can see the gas bubbles evolving. So those are the air bubbles, air being removed from water. So when water boils, the solubility decreases. Because of that, air is removed from water. So you can see that happening. I will hold it for some more time, so as to make sure the air is removed completely. So we can remove the air from water. So now that we have boiled the water properly, I will place it here. So while the water is hot, air will not dissolve in it. So now that we have the boiled water here, the normal water there, I will put both the iron nails into it. So into the normal water and into boiled water. So then we will have to have a layer of coconut oil over it, so that air does not dissolve back again. So here you can see students, the layer on top is the coconut oil layer. Here it's the boiled water and that's the iron nail. Here we have the normal water and iron nail. So this boiling tube has water that has air dissolved in it. But this particular boiling tube has water that does not have air dissolved in it and a coconut oil layer over it. But the iron nails are similar in size and they are clean iron nails. So this is the setup, students. Now this takes about 2 to 3 days for us to see the observation. So because of that, I have already prepared 2 test tubes. One with normal water and iron nail. The other one, like how I did now, boiled water with an iron nail and then coconut oil layer over that. Now we will look at those 2 boiling tubes to see what will happen after a few days. So now I have the activity that I did about 3 days back. So here you can see now this is the oil layer on top. So from that you can identify this is the boiling tube that has the boiled water. So water without air. You can look at the iron nail. I will pour the liquids out and show you the iron nail as well. So here you all can have a look at this iron nail. It is not rusted. It is a clean iron nail. So there is no rusting. Now if we take this one, the boiling tube that had the normal water. Now here you can see even the water is slightly colored, and from here itself you can see the rusting that has taken place in the iron nail. So here now here you can see this iron nail. It has undergone rusting. If we compare the two iron nails, now can you all see a clean iron nail and a rusted iron nail. So this is the one that was put in boiled water. So boiled water, there is no air, so there was no rusting. But normal water has air dissolved in it, so rusting has taken place. From this observation, we can confirm and say that for rusting, air is essential, or air is essential for rusting. So that is what you can understand from this activity. So one factor that is needed for rusting is air, or air is essential for rusting. Okay students, so now we are going to do this activity in order to examine what component from air is essential for rusting. So to do that activity, I have partly made the setup. Here I have a trough with water and there are two stands so that we can fix the test tubes. Now here I have two test tubes, and also here you can see students, I have iron wool. So this iron wool is what we are going to use to observe rusting, and what we will do is we will insert the iron wool. This iron wool, you can see now it is very clean. There is no rusting, no rust in the iron wool. I am going to insert this into one test tube. So that is going to be one setup. Then I have another test tube without iron wool. So what we will do is we will invert both the tubes and we will attach them to the stands separately. And the test tubes will be immersed in water. So initially, if I invert this, this will not come off. So here you can see we will fix the test tube here, and then I'm going to invert the other tube, and that also I'm going to fix it here. Now you can see both the test tubes and the water levels inside the test tubes are equal. So this is the setup. In one test tube we have clean iron wool. In the other setup, other test tube, we don't have any iron, any substance that is made up of iron, only the air is there. So we will leave them as it is for about 3 days, and then we will observe what happens after 3 days. So okay students, so now after few days, that is about 3 days, now you can see the change that has taken place. Can you see any change here? There's no iron wool there and there is no change there. The water level, everything is the same. But here, can you see what has happened? Look at this point. The water level has risen inside the test tube. Why does that happen? There is a component of air that has been used up by the iron wool and it has rusted. Here if you can't see it clearly, after I explain this, I will take the iron wool out and show it to you all. So here you can see there is a change that has taken place. Iron wool has rusted. For that, it has used a component from air. And look at the volume. If we look at the volume, this is about 1/5 of the air that is present inside the test tube. What is 1/5 of the air? 20%. 20% is oxygen. So from that, you all can understand that oxygen from air has been used up during rusting. That is why 1/5 of the test tube, the volume of air that was there initially, has been filled up with water. So now we will remove the test tube and observe the rusting that has taken place. So here I'm going to take the iron wool out. So now can you all see the iron wool that has rusted a little bit? Is that clear to you all? So here you can see the rusted iron wool. So from that you all can understand that iron has rusted, and for that it has used up oxygen from air. So oxygen is the component that is essential for rusting from air. We already know that air is essential, and now we all know that oxygen is the component of air that is used up for rusting. Okay students, so now we are going to do this activity in order to observe the requirement of water for rusting. So far we have been doing different activities. You already know for rusting, oxygen is needed, air is needed. From air, oxygen is the component that is being used up. So now we will try to understand whether we need water or not. So to do that activity, we need 2 boiling tubes, which I have here, clean boiling tubes. And here we have calcium chloride, anhydrous calcium chloride. You all can see here anhydrous calcium chloride, that is a white color crystalline substance. Now the function of anhydrous calcium chloride is to absorb water from air. If you keep it exposed to air for a long time, it will absorb water or the moisture in air. So what we will be doing is we will be taking a small amount of calcium chloride, anhydrous calcium chloride, into one of the boiling tubes, and to the other one we will have the boiling tube as it is. Then I have already made this setup where you can see similar iron nails. We need 4 similar iron nails which are connected to the cork. But you all know students, before connecting it to the cork, what should we do? Now what we buy from the shops, the iron nails are coated with zinc. So because of that, to remove the zinc layer, you have to soak them in dilute hydrochloric acid for about 10 to 15 minutes. That I have already done. So now I have the dry iron nails fixed this way. You can see now one iron nail, the head is here. The other iron nail, the head is inside. So this is how the cork is going to go. So there's one head of the nail outside, one tip of the nail outside, and the inside also one head and one nail. What is the reason? Now we just want to make sure that the structure of the iron nail or the shape of the iron nail does not have any effect on rusting. So to remove any effect from the shape of the nail, we do this because we are not putting the iron nail into the boiling tube. We are going to fix it this way. So like I said, now one boiling tube, just the iron nails fixed together. So to make sure there will be no air going into the boiling tube, any additional air going into the boiling tube, we put a small amount of either wax or glycerine just to make sure nothing goes in or comes out of the boiling tube. So that is fixed. Here also you can see the layer of wax so that air does not go into the boiling tube. So before I fix that, I will put a small amount of calcium chloride here. So then I will fix the cork with the iron nails. Now can you all see? Now this one has calcium anhydrous calcium chloride in it, and this does not have anything. So there is enough air inside this boiling tube but I have on my this hand. Then here also there is air, but the water or the moisture from air will be absorbed by calcium chloride. So like this, we will leave the two setup for about 2 to 3 days and then we will have to observe it. But I have already prepared this setup 3 days back. So I have the observation. I will show that observation to you all now. Okay, students. So this is the setup I just made, but this is the same activity I made 3 days before. So now we will look at the observation. Now here this is the boiling tube that does not have anhydrous calcium chloride. If I remove the cork, now can you all see? Now this side both iron nails have rusted and on this side also you can see both the iron nails have rusted. I am sure you all can see that clearly. So then here this is the boiling tube that has anhydrous calcium chloride. Now if we look at the iron nails there. Here you can see the wax also the same way I made it. Now here you can see the outside it is rusted. Look at the inside. Inside the nails, the part of the nails which were inside the boiling tube, there is no rusting. Can you all see that clearly? Now you can compare this and this as well. Inside is rusted in this one where there was no anhydrous calcium chloride. The second one, there is no rusting in the part of the nail that was inside the boiling tube. So that is the main observation. From that, what can you all conclude, students? Now in both setup, the part that was exposed to the external environment, that is the atmosphere, there is enough moisture in it, there is enough oxygen. So because of that, they get rusted. And in this tube, where there is no anhydrous calcium chloride, there is water vapor as well as oxygen inside the boiling tube. So there has been rusting. But in this tube, where you have the anhydrous calcium chloride, where we had anhydrous calcium chloride, there is oxygen but there is no moisture. So that means there was no chance of rusting. From that we can conclude and say water or moisture is essential for rusting. Okay students, so now we are going to do this activity to examine how acids affect rusting. So to do the activity, so here I have 3 clean iron nails which are similar in size and shape. You can see that. So like we did before, if you feel that this is coated with zinc, what we do is what we buy from the shops, they are usually coated with zinc. So what we will do is we will have to just soak it in acid for 10 minutes. Then you have to wash it well and dry it, and you need to have clean iron nails. That's the main thing. It has to be clean iron nails. Then I have 3 test tubes here. I have labeled them. You can see this is labeled as water. The first one labeled as water. So into this test tube, I'll be taking normal cold water. Then here the second one, you can see I have labeled this as lime juice. So into this I'll be taking water, normal cold water. With that I'll be adding a small amount of lime juice. You all know lime juice is acidic, but the acidity of lime juice is less compared to this. This is dilute hydrochloric acid. So here I'm going to take dilute hydrochloric acid. You all are familiar with strong acids and weak acids, students. Dilute hydrochloric acid is a strong acid, whereas this lime juice, which has acetic acid, is a weak acid. So then I have the 3 solutions or the liquids here. This is water, this normal cold water. Then I have lime juice here and hydrochloric acid there. So what I will do is I will take water into the first tube. Then I'll take water and add a small amount of acid there. And into this water with hydrochloric acid. Take. more water. Here it's going to be only water. And we will add hydrochloric acid. So this is only cold water. Then this one, water with lime juice, and the third tube, water with hydrochloric acid. Into all three, I am going to put one clean iron nail each. We have prepared the setup. We have to let this to stand for 1 day. So with water, lime juice and acid, we have to stand it for 1 day, and then we will observe what will happen. So to observe this, I have already prepared a setup yesterday. I will show you all the observation of that particular setup now. Okay students, so this is the activity I prepared yesterday. Now you look at the observation. This is with only water. Only cold water iron nail. You can see the iron nail has rusted, and you can see a change in the color of water as well, because the rust dissolves in water. You can see it as a light brownish color. Then I have the next tube. This is with lime juice. So here you can see the iron nail has rusted more compared to the first one. And here also you can see there is rust deposited at the bottom of the test tube. Can you all see that clearly? Then the third tube, where I have taken water with hydrochloric acid, can you see the amount of rusting there? Look at it clearly. The solution is way more darker in color, and also you can see that the iron nail has rusted a lot. So if we compare all three, if we compare the three test tubes, can you see that? With water, there is a certain amount of rusting. Then with lime juice, there is little bit more rusting. And with hydrochloric acid, the amount of rusting is high. Is that clear to you all? So from that, what can we conclude, students? Now just normal water, there are other factors, oxygen and water. So there is rusting taking place. But when we add lime juice, which has acid in it, a weak acid, so the amount of acidity is less. There the rusting was more. So that means lime juice has increased the rate of rusting. If you take the dilute hydrochloric acid, there the rusting is high. HCl is a strong acid. So the amount of acidity is very high, and the rusting is also high. So that means acids accelerate rusting. Okay students, so now I am going to do this activity in order to observe the effect of salt on rusting. So as a salt, I am going to use sodium chloride. And to do the activity, I have two clean iron nails here. And you are familiar with this procedure, students. If we buy iron nails from the shop, if it is a commercially available iron nail, usually it is coated with zinc. So to remove that zinc layer, what we do is we soak it in hydrochloric acid for about 10 minutes. And then you have to wash it with water, and then you have to dry it. So I basically have the clean iron nails here, and we have to make sure there is no rust on the iron nail, and they have to be of equal size and shape as well. So that is one material. Then I have two test tubes here. I have labeled one as water because I'll be taking cold water into this, and to the second test tube we will be taking sodium chloride mixed with water. So that is this test tube. So here I have two beakers, one with water and the other one with sodium chloride solution. So I'm going to take water into the first test tube. And to the second one, sodium chloride solution. If we take almost equal amount of solutions, it would be better. So right. So then we have to put the iron nails into both the test tubes. And we need to leave this setup for 1 day. We have to stand it for 1 day to see the observation. So one with water, normal cold water, inside that an iron nail, and the second tube containing sodium chloride solution, and in that also a clean iron nail. So to show you all the observation, I already prepared a similar setup yesterday. So I will show you all the outcome of that setup. Okay, students. So now we will look at the activity that I prepared yesterday, the same setup. So one water, normal cold water with an iron nail in it, and the other one sodium chloride solution with an iron nail in it. Now look at the first test tube. With water, iron nail and water, can you all see that the iron nail has rusted? This is in 1 day. You can see the nail has rusted, and you can see the slight color change in water as well because of the rust. If we compare this with the second test tube, the one that has sodium chloride solution, can you all see the difference? Now, in the solution, that is sodium chloride solution, the amount of rusting is comparatively high. I am sure you all can observe that clearly. So, from these two observations, now there is water and there is oxygen. So, both nails have rusted, but here it's only water, and in the second test tube, there is sodium chloride, that is salt. And in the presence of salt, the rate of rusting is very high. So from that, we can conclude and say that the salt accelerates rusting, or the presence of salt increases rusting. I'm sure you all can understand that. Okay, students. So now I'm going to do this activity in order to observe the effect of bases on rusting. So far we have looked at the effect of acids and salts. Now the effect of bases on rusting. So here I have two clean iron nails. You can have a look at the iron nails. Here you can see they are clean and are almost the same size, similar in size and shape. And we all know if we are buying the commercially bought iron nails, usually are coated with zinc. So to remove that zinc coating, we soak the iron nails in dilute hydrochloric acid for about 10 minutes, and then you have to wash them off clearly, very cleanly, and dry them. So I have very clean iron nails here. Then I have two test tubes. I have labeled one as water, the other one is labeled as NaOH, sodium hydroxide. So you all know sodium hydroxide is a strong base. And here I have water, normal water, and sodium hydroxide solution. So this is what we need to do. We need to take the two liquids, water, into one test tube and sodium hydroxide solution into the second test tube. Almost equal. We don't have to measure the volumes, but almost equal volumes. And then into both, I have to put the clean iron nails. So into water and into the NaOH solution. So I have to leave this setup to stand for 1 day. Now that I have prepared the setup here, but yesterday I already prepared another setup so that I can show you all the observation. I will show you all that observation now. Okay, students. So now here I have the observation, the same setup prepared yesterday. Now here you can see water with a clean iron nail. I put a clean iron nail in first and NaOH solution with an iron nail. Now you all can have a look at the observation. Now look at this test tube with water and iron nail. Can you all see the small amount of rusting that has taken place there? You can observe the rust on the iron nail as well as the color of the water. It has become slightly brownish in color. So that means there has been rusting. Now we will compare this with this second one. Look at this tube. NaOH solution and look at the iron nail. Can you see any rusting? Do you see rusting? No. The solution is also clear and the iron nail is also still clean. There has been no rusting. You can compare and look at both of those as well. In water, there has been rusting. In sodium hydroxide solution, there is no rusting at all. So, what can you understand from these two observations? Now, both iron nails were similar. They both have air and one is in water, the other one is in sodium hydroxide solution. In water, there is rusting. But when there is sodium hydroxide, which is a base, it prevents rusting. Or we can say it inhibits or decreases the rate of rusting. In the second tube, there is no rusting. So that means sodium hydroxide has prevented the occurrence of rusting. So bases reduce the rate of rusting. That is the conclusion of this activity. Okay, students. So now I am going to do this activity to observe the effect of other metals on corrosion of iron. To do the activity, we have a lot of materials that are needed to us. Now, I have a beaker with water, about 250 milliliters of water. And then I have a spirit lamp. You can use a Bunsen burner as well in order to boil the water and prepare the mixture. So, we have a glass rod as the stirrers. We need to mix the solution with the contents being added to it, so that it doesn't clot or become solidified. It has to be a uniform mixture. So to do that, I have the glass rod there. Then I have the rest of the materials here. You can see phenolphthalein is an indicator. You are familiar with acid-base indicators. Now phenolphthalein is a colorless solution that turns pink color in the presence of OH- ions or bases. So phenolphthalein is an indicator. Then I have potassium ferricyanide solution. Now here you can see this is potassium ferricyanide solution. Now the use of potassium ferricyanide is that in the presence of Fe2 plus ions, that is ferrous ions, when there are ferrous ions, potassium ferricyanide gives a blue color. So now you are familiar with the process of corrosion, rusting. Now there is iron, Fe, it loses electrons, undergoes oxidation and becomes Fe2 plus ions. So when that happens, when there is Fe2 plus ions in the medium with potassium ferricyanide, there will be the appearance of blue color. Then we have sodium chloride here. Now sodium chloride is also added to the mixture. It provides ions. Now you all know normally sodium chloride accelerates rusting, or the reaction of rusting is facilitated by the presence of sodium chloride salt because they have ions. Sodium chloride ionizes easily. So that is the function of sodium chloride. Then we have agar. Agar, this is the agar powder. Now you all are familiar with this. Agar can become like a jelly-like substance. Now when you add agar into hot water or boiling water and mix it well, it dissolves. But if we pour it into a container and let it to stand for a few hours, it solidifies and becomes like a agar jelly, gel-like medium. So that is the purpose of using agar. Then I have the different metals. Now here you can see I have 5 similar size iron nails there and different metals. Now these are the iron nails. You can see that. Then I have different metals here. I have magnesium. Then we have zinc metal. Then I have copper metal. And I have lead there. 4 different metals. So what I'll be doing first is I'll be setting these iron nails inside these 5 petri dishes. Now I have labeled them as well. Here you can see the first petri dish, it's only going to have the iron nail there. Then the second petri dish, it's iron and magnesium. So I'll be placing the iron nail and on that I will have to place the magnesium so that it is very much in contact with the iron nail. You have to place the second metal so that it is very much in contact with iron. Then I have iron and zinc, the third petri dish. So here iron and zinc. You can see the iron nail, the zinc is touching the iron nail. I have actually folded one end of the zinc, the other metal, so that you can pass it through the iron nail. So they are completely in contact with each other, iron and zinc. Then we have iron and copper. The same way, I will insert the iron nail through copper and place it like that. So iron and copper. And the last one is iron and lead. Iron and lead. Iron and lead. So here we have iron and lead. So this is how we have the 5 different petri dishes. First one, only iron, that is to confirm that there is rusting taking place. And here in all 5 petri dishes, we have iron nails which are very clean, similar in size and shape. So 5. First one only iron, second one iron and magnesium, third one iron and zinc, then we have iron and copper and iron and lead. Now you all can remember the activity series, students. Magnesium and zinc, they are above iron in the activity series. Copper and lead, they are below iron in the activity series. So that is how we select these 4 metals. Now we have to prepare the medium, the agar medium. To do that, now first I'll need to boil water. When it is becoming hot, we will add sodium chloride, potassium ferricyanide and phenolphthalein into water. And we have to bring it to boiling point. Now there is something you all have to remember, students. Although according to the procedure, we add phenolphthalein into water and then boil it. But the thing is, phenolphthalein has the tendency to quickly evaporate off due to its composition. So because of that, while boiling, sometimes we can lose a small amount of phenolphthalein or all the phenolphthalein because we are adding few drops. So to compensate for that, what I will do is, after mixing the agar also, I will add a few drops of phenolphthalein to the mixture. So to that, I will need to add this yogurt spoonful of sodium chloride would be enough. That and a few drops of potassium ferricyanide and also a few drops of phenolphthalein. So to water, I have added sodium chloride, potassium ferricyanide and phenolphthalein. Right. Now we need to mix it so that these substances dissolve well, and also we need to bring it to boiling point. Need to allow it to boil. until it boils. I'll keep all these to a side. So now you can see the water starting to boil. But we need to bring it to boiling itself before I start adding the agar. We'll let it to boil for some more time. So just to recall what we did, into about 250 milliliters of water, I added 1 yogurt spoonful of salt, that is sodium chloride, so that it provides ions to the medium. And also you all know, normally salts, because of the ions, they accelerate or increase the rate of rusting. So they facilitate the anodic and cathodic reactions. And also we have potassium ferricyanide in order to give color, blue color, when there is Fe2 plus ions present. So if iron nail undergoes oxidation, then potassium ferricyanide will give a blue color. And the addition of phenolphthalein in order to observe the formation of hydroxide ions. When there are OH minus ions, phenolphthalein gives a pink color. And now I will have to add the agar. Here you can see the agar powder is there. If I add that and make a solution in hot water, boiling water only, agar will dissolve well and we will get a homogeneous mixture. After that, when we pour the agar into all these 5 petri dishes, it will solidify. That will take about at least an hour to do, hour for the agar to solidify and give a gel-like medium. So still we need to allow the solution to boil properly. So in this there is water, potassium ferricyanide, sodium chloride and phenolphthalein. Okay students, so it's almost closer to boiling. Then I will start adding the agar. You have to add little by little while mixing it completely. Otherwise, the agar will solidify in clumps. That is not very useful for us. It has to dissolve completely. You have to add agar little by little and make sure it dissolves. We need to add about 1 teaspoonful of agar. So that is what I have taken here. So now that I have transferred all the agar powder into it, we have to mix well so that it dissolves completely. So now that the agar is completely dissolved, we have our mixture ready. I will have to take it off from the burner and then I'll have to pour it into the petri dishes. So now we have the mixture ready. You all know what the contents are. Water with potassium ferricyanide, phenolphthalein and sodium chloride salt. Thereafter, I added agar and the agar has dissolved completely. So there is no clumps of agar or any solidified particles there, I can pour them into the 5 Petri dishes here. So while pouring, it's better if I can keep the glass rod and pour it onto that so that the solution doesn't spill. So that is for the iron nail. We have to make sure the metals are completely covered in the solution. So then the next one, iron and magnesium. Then we have iron and zinc. Then I'll pour into iron and lead. And then here we have iron and copper. We have to make sure the metals are all immersed inside the mixture. Now here you can observe, students, while I poured the solution itself, you can see the formation of the color, the pinkish color around iron nail. But the others, of course, we cannot see the color change. Anyway, we will have to wait for about at least 1 hour until the agar solidifies and until the changes take place. So what you need to observe is the appearance of pink color, appearance of blue color, whether they are there, and if they are there, around what metal is the color present. So you have to look and see whether there is blue color near the iron nail or pink color near the iron nail or the metal. Those are the observations that you have to look for. So we will observe this after 1 hour. Okay, students. So you all have understood how we made the activity, how we prepared all these Petri dishes containing the 2 different metals. So as you can see here, it's only the iron nail. And you can remember, to the agar medium, what did we add? We added the phenolphthalein indicator, which gives a pink color with hydroxyl ions, as well as the potassium ferricyanide that gives a blue color with ferrous ions, Fe2 plus ions. So if we look at the first setup here, that is only the iron nail. Can you see here at the 2 ends of the nail? You can see the blue color regions clearly, but in the middle you can see the pink color is faintly visible. So what has happened here? At the 2 ends, iron has got oxidized and the Fe2 plus ions have been formed that give the blue color with potassium ferricyanide. Whereas in the middle, water and oxygen react together and undergo the reduction reaction that forms the hydroxyl ions. So that gives a pink color with phenolphthalein. Can you all observe that clearly? You can see it here as well. So this is only iron. Then we use different metals to protect the iron. That is what we wanted to observe. So here you can see the first 2. The observations are similar. That is the first, this setup with iron and magnesium metal. Magnesium is above iron in the activity series, as well as iron and zinc. Zinc is also above iron in the activity series. Now observe what has happened. Can you all see the colors, students? Here you can see the pink color near the iron nail. And there is no blue color formed in the medium. So that means only OH minus have been formed near the iron nail, and there the iron nail has acted as the cathode, because the formation of OH minus is the reduction reaction. But there is no change in iron. The same thing here. When there is zinc, Oxidation takes place at the zinc and reduction of water and oxygen forming hydroxide ions take place near the iron electrode. So there again iron has become the cathode. So in these two, where we use magnesium with iron and zinc with iron acts as the cathode. So we call that method of protecting iron as the cathodic protection. And here magnesium and zinc are the sacrificial electrodes. They sacrifice themselves to protect iron from corroding. Now if we come to the last two activities, here you can see iron and copper. Copper is below iron in the activity series. The same way iron and lead. Lead is also below iron in the activity series. Observe the changes here. You can see near the copper plate there is pink color. That means OH minus ions have formed there and that is the cathode. Whereas here near the iron nail you can nicely see the blue color region, that is due to the potassium ferricyanide reacting with ferrous ions. So that means iron has acted as the anode. So copper is the cathode, iron is the anode. The same way with lead and iron. You can see near the lead plate again there is pink color. So presence of OH minus ions, that means the lead has acted as the cathode, and near the iron you can see blue color, that is the presence of Fe2 plus ion. So that is the anode. So in these two instances where we use copper and lead, if there is a full coating over iron, then the oxygen is not in contact with iron and iron doesn't corrode. But if there is a scratch and if iron is exposed to oxygen and water vapor, what will happen is both the copper and lead will act as the cathode and iron will undergo oxidation. It will act as the anode, so it will undergo corrosion more. So the best way to protect iron is to use either magnesium or zinc. So those are the sacrificial electrodes. So can you all understand the observations clearly, students? Again, you all can look at the colors clearly. Iron nail only, iron and magnesium. Near the iron it's only pink color, iron and zinc. Again near iron it's only pink color, so that is the cathode. And here when it is iron and copper, iron reacts as the anode, and again with iron and lead, iron reacts as the anode. So those are the ways of protecting iron from corrosion.